All right, so let's talk about the last section in 7.1. We're going to talk about intermolecular forces and how it impacts states of matter. Now, just a quick reminder here, intermolecular forces, IMF, are those attractive forces. They pull molecules together. Attractive forces between neighbors, not within a molecule, but between the neighboring molecules. And if you look at this little animation that's up on the screen, it's all those little white flashes of light. Those are the forces pulling neighboring molecules together. And some molecules have that, especially if they're polar, they will be attracted to one another. If they're nonpolar, they're not going to have this kind of attraction. So they're not going to be pulled together. They don't have this kind of IMF. Now, the strength of the intermolecular force is responsible for whether or not a substance is a solid, a liquid, or a gas at room temp, or at any temperature for that matter. And it also determines how much energy must be added or released in order for a phase change to occur. So you see Olaf there. He hasn't quite melted yet, but you can imagine that if he laid there for a little bit longer, he probably would melt. How much energy is required to melt him? Now, is that beach ball going to melt, or is that umbrella going to melt, or is that sand going to melt? No, and there's different intermolecular forces in those substances than in the ice that makes up Olaf. So what we're looking at here is what's going on with those intermolecular forces, how strong are they, and how do they determine what state of matter, and how we can get some phase changes, melting and freezing and boiling and condensing and so forth. How do we get that to happen? So that's where we're going here. All right, so if you take a look at the three states of matter, we got solid, liquid, and gas. Now compare solids, the motion of the particles, to the liquids, and then to the gases. And there's a lot of obvious differences there, but the biggest thing you should be imagining are those little flashes that you just saw on the previous screen. In a solid, those flashes would be unbelievably bright and they would be all over the place. And I can't really show you or animate it here, but they would be here constantly and here constantly and here constantly and here constantly because the particles are so close. There's really strong intermolecular forces. That's what keeps those particles together. Here, the intermolecular forces still exist, but they're a little bit weaker. This particle right there, if I try to follow that one around, that particle might not be super strongly attracted to that one that used to be over there. You can see it moved on me. But those intermolecular forces exist, they're just a little bit weaker than in a solid. And gases, this is important, have no intermolecular force. This particle down here has zero attraction for any of these other particles because it's so far away. Now, when they do get really close or they slow down, well, then they start looking like a liquid and acting like liquid. But when they're doing their thing and super, super far apart from one another, which gas particles are, then there's no attraction. They're too far apart. They can't possibly be attracted to one another. Now, what we want to think about, and we're going to look at a little simulation here, is how does changing the temperature, remember temperature is the amount of energy something has, how does changing the temperature impact those intermolecular forces? So here are a bunch of water molecules, and they're at a certain temperature. I don't know what it is, but the thermometer shows us that. Now they're bouncing all over the place, and they're kind of hard to keep track of, so I'm going to slow them down. What I want you to look for are the intermolecular forces. Not what's holding each of the particles together, not what's holding that hydrogen to that red oxygen, but what's happening with like these two neighbors. See those little dotted lines? Those are the intermolecular forces. Now this guy right now has no intermolecular forces with anybody, and now he does. He got a little closer, and you can see those dotted lines appear. But like this guy down here, he has no forces, now he does. So intermolecular forces exist between neighbors. Now, how does changing temperature affect this? Let me add heat. Watch what happens to the intermolecular forces. Actually, let's do cool first. I'm going to slow these particles down even more. What I want you to think about is how much motion is there and how long are they connected to their neighbors with those intermolecular forces. Those dotted lines stick around a lot more, and you see that because they're connected, because they're attracted to each other, they're all kind of hanging out in one big group now. So taking energy away, cooling a substance down, this is important. It slows the particles, they get closer to one another, and those intermolecular forces get stronger. It keeps those particles together. The dotted lines stick around a lot longer and are a lot stronger. That's when we cool it down. Now watch what happens when we heat it up. We're going to add energy. The particles are going to start wiggling faster and faster and faster. And now they can't hang on to one another as easily. So now the intermolecular forces do exist when they get really close, but they don't stick close to one another for very long because they have so much motion and those intermolecular forces aren't real strong. So cooling them down makes those intermolecular forces stronger. The particles hang on to one another a little bit longer. That's what an ice cube would look like. Particles really close. And then if we heat it up, these are like crazy hot water particles turning into a gas, bouncing all over the place in the air, and they're not even connected to one another. So let's go back to our notes here. We're going to talk about phase changes here. Now you guys all can deduce that Olaf here, if he gets a little too close to the fire, he's going to be gaining energy from the fire. He's gaining that heat. The ice particles, the water molecules that make up his body, are going to start vibrating faster and faster and faster, and they're going to do what we just saw in that animation. They're going to start moving around more. They're not going to be as tightly connected to one another as much, and he's going to eventually start melting. So we're going to be looking at phase changes. Now, we're going to see two slides here. The first slide is adding energy. This is what's happening to Olaf. He is a solid. He is like these solid particles, just vibrating really close, really strong intermolecular forces. And if we add energy, we go from a solid, still solid, still solid, but then we hit this solid line right there. That marks the point or the temperature at which it starts turning into a liquid. And then as soon as we're done turning into a liquid, melting, now we're a liquid. And we stay a liquid in this range. And then we go up, 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 up. And then we get to another magic point at which it vaporizes, or it turns into a gas. You guys are familiar with this. We call it boiling at a certain temperature and pressure. But it's a liquid, 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 and then it hits a boiling point, and this is when it's turning into a gas, and when it's all done boiling, it's all gas. So, as you add energy, the solid becomes a liquid, the liquid becomes a gas. Why? Because the motion is increased, the intermolecular forces get weaker and weaker and weaker until there are no intermolecular forces all the way up here at the gas. And obviously that extra energy causes those particles to move faster. The intermolecular forces can't keep the particles together, and a phase change occurs. So the faster these molecules in the ice move, the more it's going to melt. Then it turns into liquid. Imagine liquid water in a puddle. You know that that's going to evaporate. The sun will beat down on that, give it some energy, and then those particles will break free from the rest of the liquid particles held together by weak intermolecular forces. And as soon as they break free, they turn into a gas. And gases zip around up here in the atmosphere, and they have no intermolecular forces. So that can happen through evaporation, or it can happen through boiling. That's adding energy. That's Olaf getting close to the fire. Now, we could do the opposite. We could take energy away. Imagine if poor little Olaf melted. Well, you could put him in a freezer. The freezer's job is to remove energy from warm things until it gets cold. So, if we start off with some water vapor, let's imagine you go and take a ridiculously hot shower. There's some hot gas particles zipping around in the air, and they hit the nice cold mirror. What happens? Well, they condense. They lose some energy. They lose energy, goes into the mirror, because the mirror is a little cooler than they are. The intermolecular forces get stronger. It pulls those particles that used to be gas, it pulls them together, and it turns them into liquid. Call that process condensation. You can imagine seeing this outside in the summertime. You wake up and you might see dew on the grass or on your windows. But if it gets cold enough, that liquid drops, like the temperature does, and then it hits a temperature at which it freezes. And now we call it frost. So this is the same as this. It's just undergone another phase change. It lost even more energy, and the intermolecular forces got even stronger. So as you go down, the intermolecular forces get stronger and stronger and stronger. On the previous slide, we looked at going up, intermolecular forces getting weaker, 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 until there's no intermolecular forces. So changing the temperature, changing the amount of energy, will change the intermolecular forces. And last idea here is that there are just some substances that really have strong intermolecular forces, just naturally, just because of the way the molecules are, the polarity, and so forth. Some have really strong intermolecular forces, and it requires a lot of energy to break them apart and to cause them to change their phase. So if you want to get a solid to melt, you might have to add a lot of energy. Think about a piece of metal. If you want to get metal to melt, you got to add a lot of energy. If you want like candle wax to melt, you don't need to add as much energy. There's different levels of intermolecular forces or different strengths. Think about water. If water was poured on your skin, that water would eventually evaporate, but it might take a little while. If we put that water in a pot and wanted to boil it, we would have to raise the temperature to 100 degrees Celsius if we wanted to boil all of that water all at once. Now, let's take a look at alcohol. Imagine getting a shot at the doctors. They usually wipe off your arm first with some rubbing alcohol. Now, within seconds, let's imagine that this nurse moves a little gauze. They've finished cleaning your arm. They're ready to give you a shot. Your arm probably feels very cool at this point, and it's dry. Why? Because those alcohol particles wiggled faster, faster, faster. They gained energy from your nice warm arm, and bing, 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 they started turning into a gas and escaping and leaving. The boiling point for rubbing alcohol is less than water. If the nurse rubbed your arm with water and took the gauze away, your arm would still be wet. It doesn't escape as quickly because the particles are held together tighter, stronger intermolecular forces. This is strong, holding them together. These guys escape quickly because there's weak intermolecular forces holding them together. It doesn't require as much energy, less energy to cause a phase change. It's easier to break those particles apart and break down that organization. So they have lower melting points and boiling points. We're going to look into this a little bit more later in the year, but you just have to know that different substances have different strength intermolecular forces, but if you do add energy, you can change the phase by weakening those intermolecular forces, making the solid become a liquid, making the liquid become a gas. If you remove energy, then the particles slow down, and then you can go from a gas to a liquid to eventually a solid, and the intermolecular forces will get stronger. So changing the amount of energy will change how the intermolecular forces impact what state of matter you have.